Good evening, everybody, and welcome to the class. Today, I shall solve a problem related to the moment of inertia for the cross section you see here. It's basically a rectangular cross section which has a width of 500 millimeter and a depth of 700 millimeter. It has a hollow rectangular portion, uh, 300 millimeter wide and 250 millimeter deep. There is also a hollow semicircle portion which has a radius of 100 millimeter, and because we have to determine the moment of inertia about the centroidal x and y axis, that's why we should first locate the centroid of this cross section. If you look at this cross section closely, you will see that there is an axis of symmetry right here. So centroid should be somewhere on this axis of symmetry. So horizontally the centroid is known, but vertically we don't know where the centroid is. So first what I shall do is I shall draw the axis of symmetry, so that, yes, right here I will draw this axis of symmetry. So this can be our centroidal y-axis, but vertically where we have the centroid, that we don't know because there is no horizontal axis of symmetry. So our calculations will begin with the determination of the centroid, and for the centroid we must choose a reference axis, and I will use this axis right here, right at the bottom, as my reference axis, and all the um, y tildes will be with reference to the base. So first thing, let me write down the formula for y bar. Y bar is equal to summation of y tilde a over the summation of the areas, right? So for this purpose we'll have to divide this shape into some basic shapes, and there are multiple ways you can divide it into basic shapes, but what I shall do is I shall divide it like this because this is 700. So I will continue this to make a rectangle which is 100 millimeter wide and 700 millimeter deep. Exactly in the same manner I will divide it here and continue it up to here. Now we have total 5 areas. Let me number them: 1, 2, which are actually same, and this one is 3. Then this rectangle which includes this semicircle is number 4, and this one will be numbered as 5. So there are total 5 areas. It means if you expand this, you will have y1 tilde a1, y2 tilde a2, plus y3 tilde a3, y4 tilde a4, and then plus y5 tilde a5. This a5 is for the hollow semicircle, and ultimately it will be subtracted. Similarly here, a1 plus a2 plus a3, a4 and a5 will be subtracted as well. So first of all I shall determine the areas, and if you see, the area number 1 and area number 2 are exactly same dimensions, 100 by 700. So a1 will be 100 by 700, which is 70,000 millimeter square. This is also equal to a2. a3 is a rectangle, horizontal dimension is 300, vertical is 80, so a3 will be equal to 80 by 300. that should be 24,000 millimeter square. Then A4 is this rectangle, which is again 300 millimeter wide and 370 millimeter deep. That is A4. So A4 is 300 by 370, and that will be equal to 111 millimeter square. And the last one is A5, which is a semicircle. A5 will be pi r square, r is 100, divided by 2 because it's a semicircle. So you will get 15,700 millimeter square. So these are the areas for all the 5 segments. Now we shall determine the individual y1 tildes. So y1 tilde and y2 tilde will be exactly same, and that will be with reference to this base. The height is 700 millimeter, so the centroid will be at the mid height right here. Somewhere here will be the centroid. So from the centroid of area 1 and centroid of area 2, somewhere here, it's actually 350 somewhere here. So half of 700 is 350 from here, and from here that will be our y tilde, y1 tilde. So I will write it as 350 millimeter. Okay, and then y2 tilde, sorry, y3 tilde, centroid for the area number 3, which is a rectangle, will be at mid width and mid height somewhere here. So if you see, this is total 700. So from this 700 we will subtract this small portion, which is half of 80, that is 40. So y3 tilde will be equal to 700 minus 40, and that should be 660 millimeters. Okay, then area number 4 is a rectangle again, which is 300 millimeter wide and 370. So this centroid will be at half of 370, mid height somewhere here, maybe half of it, mid height. So from here to here it's half of 370. So 370, y4 will be, y4 tilde will be 370 over 2, that is 185 millimeter. Okay, and then area number 5 is a semicircle. Semicircle, the centroid is somewhere here. For a semicircle, the centroid is located from its base at a distance of 4r over 3 pi. So from here to here is 4r over 3 pi, and then you have to add another 100 millimeter. Okay, so y5 tilde will be equal to 4r over 3 pi plus 100. So if you plug r equals to 100 millimeter, the answer you will get is 142.46 millimeter. Okay, now you have all the numbers which you can plug in this formula and get the answer. So y bar is equal to y1 tilde, which is y, now y1 a1 are exactly equal to y2 and a2. That's why we can just multiply this with 2 to cover both of them. So this is 350 into 70,000 multiplied with 2 to cover both of them, plus y3 tilde into a3. y3 is 660 into a3 is 24,000, plus y4 is 185 into A4 is right here, which is 111,0,0. Okay, and the last one is for this semicircle, so it has to be minus y5 142.46 into a5, which is right here 15,700. So this is the numerator. Then comes the denominator, where we shall add all the areas. This 70,000 multiplied by 2 to cover a1 and a2 both, so 70,000 into 2 plus a3 24,000, a4 11000. So the last one has to be negative, which is 15,700. So this is the complete calculation. Now we can just solve it to get our y bar. Okay, the answer for the centroid comes out to be 320.63. So what you can do is you can round it up and use this as 321 millimeter. Okay, now we shall determine the moment of inertia for this section, and we shall begin from Ix, that is moment of inertia about the centroidal x-axis of the cross section, and the areas which we have already divided this shape into, we will continue to use the same areas. So I will make a table here. Segment, we have total 5 segments, 1 2 3 4 and 5, and the next column, and by the way, the equation which we shall use of parallel axis theorem will be Ix equals to Ix prime plus a dy square. So the area is the simplest calculation. We shall do the area first. All areas are in millimeter square, and these are the same areas we have already determined. I will just reproduce those numbers here. The first and the second one are 70,000. The third one was 24,000. Fourth is 111,000, and the fifth one is negative, that is semicircle, 15,700. If you sum all of them, you will get 259300. So that completes the area. The next one is dy, and dy is the distance between the axis for which you know the moment of inertia and the axis for which you want to determine the moment of inertia. Now I will call these two as known and the unknown axis. So our unknown axis is this one, x, centroidal x-axis, for which we want to determine Ix, and the known axis would be the centroidal x-axis of all individual areas 1 2 3 4 and 5. If we start from the first one, for example, for the first one, the centroid is right here. So you have these two, known and the known axis. This one is x prime and this one is y prime. Same is the situation here. You have x prime and y prime. Now dy for area number 1 will be from the own centroidal x-axis to the centroidal axis of the whole shape, this small distance. We will call this as dy1, and on the same lines we have this distance called dy2, and it's very easy to calculate. The centroid for area number 1 is half of 700. From here to here is 350, And the centroid location from this green axis we have already determined in the previous section, and that was, let me write down that here, from here to here, that distance we determined was 321, and from the top, then the remaining, that will be 700 minus 321, that should be 379. So if you subtract 321 from 350, that will give you dy1 and dy2. That I shall write here. 350 minus 321 comes out to be 29. So for segment 1 and 2, the distance is same, 29. Now the area number 3, the centroidal x-axis is right here, x prime, and this one is y prime. So from the centroidal x-axis of area 3 to the centroidal x-axis of the whole shape, from here to here, this distance right here is our dy3, and you can easily calculate by subtracting this small distance of 40 from 379. So let me write down it here. 379 minus 40, that comes out to be 339. Then the area number 4, right here, it is area number 4 is 370 millimeter deep, so its centroid will be half of it, 185. And by the way, it's not here, I mistakenly mentioned it here, it's somewhere here for this rectangle. So from here to here, this distance is our dy4. Okay, and you can easily calculate it by subtracting this distance, by subtracting half of 370. This is 370, so this is half of 370. Subtracted from 321, the remaining distance will be dy4. So that will be 321 minus half of 370, that will be ultimately 136. And the last one is for the semicircle. Centroid for the semicircle is here, this is its x prime. So from the centroid of the semicircle to this centroid of the whole shape, this distance is dy5, and we can easily calculate it by subtracting this distance, which we already calculated in the calculation of centroid, and it was 142.6. Subtract that from this 321, and the remaining will be your dy5. So that I will write here. 321 minus 142.46, and if we calculate it, we will get 186.54. Okay, now this dy is done. We will now calculate ix prime. Ix prime is very easy to calculate. For a rectangular cross section, the formula will be bh cubed by 12. B is the horizontal dimension, so horizontal dimension is 100 and the vertical dimension is 700. So 100 into 700 cube by 12, you get 2858.33 into 10 raised to the power 6, and the same will come here because they are identical. 2858.33 into 10 raised to the power 6. Now area number 3. Area number 3 is also a rectangle. B is 300, H is 80. So you have BH cubed by 12. 300 into 80 cubed by 12, and you get 12.8 10 to the power 6. Area number 4 is a rectangle. B is 300, H is 370, so B into H cubed by 12, and you get 1266.33 10 to the power 6. And the last one is the semicircle, and the moment of inertia of a semicircle about its centroidal x-axis is right here. That is basically pi into r raised to power 4 over 8 minus 8 times r4 over 9 pi. Do not forget to have this negative sign because this is a hollow area. So answer for this one will be minus 10.94 into 10 to the power 6. So these are the moment of inertia about their own centroidal x-axis. Now the last one is Ix, which is coming from here. You simply apply the equation on these numbers and get the answer. For example, this one you will get 2917.2 10 to the power 6, and this one is same 2917.2 10 to the power 6. Then this one, same process, you get 2770.9 10 to the power 6, and this one you will get 3319.39 10 to the power 6, and the last one with a negative sign is 557.26 into 10 to the power 6. Now you algebraically add all of them to get your answer of Ix. So just sum and you will get 11,367.43 into 10 to the power 6. So this is your answer for the moment of inertia of this cross section about its centroidal x-axis. And you can use this number and the area of cross section to get the radius of gyration. Radius of gyration of this shape about x-axis, kx, is Ix over a square root. Just use this 11,367.43 into 10 to the power 6 over the area 259300. Just take the square root and get the answer. You will get it 209.38 millimeter. So this is the radius of gyration about x-axis. Please redo all these calculations. There may be small mistakes, so you can solve by yourself and reconfirm this answer. Okay, so this is moment of inertia about centroidal x-axis. Now we shall move to the calculation of moment of inertia about centroidal y-axis. So though that will be done on similar lines. We'll start from here. Iy means moment of inertia about centroidal y-axis of this whole shape, and the formula using the parallel axis theorem, Iy prime a dx square. And we'll make a similar table. Number 1 is segments, 5 segments, 1 2 3 4 and 5, and the areas do not change. Areas are the same. I will just reproduce 70,000, 70,000, 24,000, 111, 000, and minus for the hollow semicircle. Then the next is dx. Okay, Now dx is the distance between the centroidal y-axis of the area to the centroidal y-axis of the whole shape. Now for area number 1, it's a distance from here to here, from the known to the unknown. This is our dx1. Similarly for area number 2, which is identical from the known to the unknown, this distance is dx2, and they are numerically same because this y-axis is right here in the middle. Total is 500, so this distance is 250. So from 250, just subtract this small distance of 100 by 2. So this will be 250 minus 100 by 2, that will be 200. And same number is for area number 2. Okay. Now for area number 3, if you see, the y prime axis of area 3 overlaps with the y-axis. That's why the dx3 will be 0. Similarly, for area number 4, its own centroidal y-axis overlaps with the centroidal y-axis of the whole shape. That's why dx is also 0. Same is the case for this semicircle. The centroidal y-axis of the semicircle overlaps with the centroidal y-axis of the whole shape. The distance dx is 0. So that's the benefit of having a symmetrical shape. Now the next one is iy prime, and iy prime for a rectangular section is h b cubed by 12. H is 700 and b is only 100, 700. So 700 into 100 cubed by 12, that will come out to be 58.33 10 to the power 6. Same is for area number 2, 58.33 10 to the power 6. Then area number 3, you see area number 3 is also a rectangle. B is 300, H is 80, so this is going to be 80 into 300 cubed by 12, and the answer should be 180 into 10 to the power 6. Area number 4 is also a rectangle with B of 300 and H of 370. So this is H into B cube by 12, 832.5 10 to the power 6. Last one is the semicircle. For a semicircle, mode of inertia about centroidal y-axis is pi r4 over 8, and you have to apply the negative sign because of the hollow area. Solve it, you get minus 39.25 10 to the power 6. So that completes the iy prime. And the last column is for iy using this formula. So use this number, this number, this number to apply the equation, and you will get 2858.33 10 to the power 6. Same comes here, 2858.33 10 to the power 6. And for these three, because your dx is 0, so this part will go away and iy prime will be equal to iy. So these numbers will directly be shifted to these columns. 180 10 to the power 6, 832.5 10 to the power 6, and minus 39.25 10 to the power 6. Now you algebraically add all of them and get the answer for iy, which will come out to be 6689.91 10 to the power 6 millimeter 4. Again, please reconfirm these numbers. There may be some small calculation mistake. Now using these numbers, this one and this one, oh sorry, the sum of the area was 259300. You can get the radius of gyration about y-axis, that is IY over area. So IY is 6689.91 to 10 raised to the power 6 over the area 25900. Solve this and you will get KY as 160.62 millimeter. Okay, and the last thing I want to calculate is the polar moment of inertia. That is called J, and it is simply equal to Ix plus Iy. Ix is 1136.743 10 to the power 6 plus Iy 6689.916. That will give you a value of J as 18057.34 10 to the power 6, same units, millimeter 4. So that will be your answer. So that completes this whole question of determining the moment of inertia about centroidal x and y axis. Thank you very much.